Hello everyone. Today I'm going to present our accepted paper on an efficient service dispersal mechanism for fog and cloud computing using deep reinforcement learning. I'm Chinmaya Dehury, research fellow at Mobile and Cloud Lab, Institute of Tartu, Estonia. So in this presentation, will go through this fog computing, cloud computing, how the service delivery is happening using fog and cloud computing. What's the problem statement? What's the proposed solution? And how we have like evaluated and what are the results? And we'll conclude with our conclusions. So if you see the cloud resources, usually how we are accessing those cloud services is we have a service layer or we have a web browser, let us say, and that one will be connected to the service layer of the cloud resource provider or cloud service provider. And over there also, like we have this virtualization layer that will establish a connection between the service and the physical resources or the virtual resources. So when a number of users increases, and also when we talk about the latency of the services, when we talk about the security of the services, we try to introduce a new layer of the computing. So similar to the cloud, we will have another layer which is in between the cloud and the user, and that will be near to the user. So if it is very near to the users, that means the latency will be decreased, and that will have a greater impact in increasing the quality of service. So if we'll take an example, let us say if I take take a video, I upload that recorded video to a fog layer, and I ask that fog layer to find a person in that video. So what fog layer will do is it will divide the whole video into 5 different slices. 2 slices will be processed by fog node, and 3 slices will be processed by a cloud node. And and also like it may happen that it will process all the slices, all the total video, and cloud will do nothing. Or it may also happen that based on the resource availability of the fog node, only 1 slice will be processed by fog node, and 4 number of slices will be processed by cloud node. So the main intention over here is that we need to reduce the latency, or we need to offload the processing to the cloud, and the fog layer should be responsible for providing service to maximum number of users. And that doesn't mean that we'll compromise with the quality of service. So keeping the quality of service, fog layer need to process only what is needed from that service. So based on the criticality of the service, based on the criticality of the person or the priority of the user, it will try to offload some portion of that video to the cloud. So that means some service are offloaded to the cloud, but fog layer will be mainly responsible for providing the service to the user. So keeping that in mind, our motivation is that what percentage of fog layer or what percentage of the service should be assigned to the fog, and what percentage of that service should be assigned to the cloud. Now, with that problem, our goal is to efficiently provide the service to the user. So how we'll do that? It's not only efficiently provide service to the user, but also provide the service to maximum number of user. That means we need to accommodate as much number of user as we can, and fog node should be responsible to provide those services without compromising the quality. So in this example, if you'll see, here we'll have user 1, user 2, user 3, user 4. Those are connected to the fog, and fog node and cloud are connected. So these two are providing 3 different kinds of services. So for example, like if user 1 is accessing those services from fog node and cloud node, and let us say the service 1 user is accessing the service 1, which is 20% will be responsible by 20% will be processed by a fog node, and 80% will be processed by cloud node. So that means if I'm accessing some kind of service, though I'm getting those service from the fog node, but behind the scene, 80% of those services are handled by the cloud, and 20% of those services are handled by the fog. And similarly, different users are accessing different services. And here you can see that the fog node here is processing 20%. Over here it is like 60%. Over here it is like 90%. So there are like different parameters up there to decide what percentage of that service should be handled by a fog node, and rest of the percentage will be handled by the cloud. So the goal over here is, or the objective over here is to minimize this value. If we minimize this value without compromising the some constraint, without compromising the quality of service, uh, we can accommodate maximum number of user. So, and this is what our goal. Now, keeping that goal in mind, what we have in our system model is we have one fog node and we have one cloud node. So users are connected to the fog node, and fog node is mainly responsible for receiving the user's request, and that will decide what percentage of that service will be forwarded to the cloud. And each fog node are connected to only one cloud. So if we talk about the users, we have a set of users that are connected to the fog node, and the number of services availing from the fog node is definitely the total number of services offered by the fog node. So each user, they are having a particular distance, they are having some certain distance from the fog node. So based on the geographical location, we can calculate what's the distance of the user and the fog node. Uh, and we have a range of the fog node. So let us say, and the fog node is able to provide the service to like around 50 the users who are within 50 or maybe let us say 40 kilometers from that fog node. So we have this fog node which mainly indicate what's the communication range between user and the fog node. And based on this distance, we can calculate what's the priority of the user. So, and this is what the example, this is what the equation we are considering to calculate the distance, or to calculate the priority of the user based on the distance. And it is saying that di is the distance of the user, and capital D is the maximum value between user and the fog node. So higher the value, higher the distance, and hence higher priority. So uh, yeah, so each user send service request to only one nearby fog node. And uh, along with the fog node, sorry, along with the distance, we'll have the latency. And latency is mainly talking about what's the round trip time, or what's the RTT value between user and the fog node. And similarly, we have the round trip delay between fog node and cloud node. So round trip RTT value uh, between fog and user is mainly var sigma of I, and priority of user based on this RTD value is is kind of like relative, and so that means it will see what is the maximum latency among all the connected users, and based on that we'll calculate the priority of the value, sorry, priority of the users based on the latency. So here, higher the value, higher the latency, that means higher the priority. So that means the priority, we can say that the user having maximum distance, or the user having more latency, will be given higher preference. So priority of user based on that latency and the distance, we can calculate the overall priority of a user. Okay. So apart from that user modeling, we have this service request. So users send the service request to the fog node only. They don't send the request to the cloud node directly. So this represent the number of slices of the service request. As we saw before, that we have uh, we have a service, and the whole service is sliced into multiple chunks. and each chunks or each slice are assigned to either fog or cloud. So uh, yeah, this represent the what's the number of slices of that service request. And if this is zero, that means user is not availing the service at all. However, if this value is greater than one, then user is availing the service, and the service type is SCAN. And if it is one, that means user is availing the service, and that service is having only one slice. You can say that the whole video is of one slice, and that video need to be processed either only by fog or by cloud node. So each service also they have some resource demand. So the resource demand is basically of two types. One is base and auxiliary resource type. Base resource type is something like what's the minimum service requirement, and auxiliary is based on the input data. So if your input data is 2 MB, then probably you need some additional resources. If your input data is 50 MB or 500 MB, then your additional or your auxiliary resource requirement will be more. So based on this base resource requirement and auxiliary resource requirement, we can calculate the total resource requirement of a service, and hence we can also calculate the total resource requirement of a particular slice. So if we know what's the total resource requirement of a service, we can divide that one with the number of slices. So but definitely the base resource requirement is minimum, and that is common to all the slices. So along with the resource requirement, each service required have their own size, and the size of a service request it is about like the number of instructions, we can say. And similarly, we can calculate the number of slices, and sorry, we can calculate the size of each slice. Now, we have seen that service request, we have seen what's the service slices. And now, if we talk about the services itself, these are mainly processed by both fog and cloud servers. And the request will be delivered by the fog, and the request will be also received by the fog node. And number of slices per service request is not uniform among all the services. If you see here, the slice it's a logical representation of a part of service request. For example, if we want to process a video of 100 MB, then one slice can be 25 MB if we are dividing the whole service into 4 slices. Now, based on the number of services and based on the number of users connected to or availing those services, we can calculate the service sensitivity. And service sensitivity it indicates how important the service is compared to other services. And we assume that this value is assigned by the fog provider. And we have the service demand. So the service demand is mainly represent how many users are currently availing those service, and that is what the service demand. So service priority we have. So service priority is mainly if the whole fog node is providing m number of services, then the service priority will be calculated based on the distance of the connected users, those are availing that service, and the latency of the users that are availing that service, and the service demand. So based on these three different parameters, we will calculate what is the service priority. And this is the equation how we are calculating the service priority. And when you talk about the service slicing, so this is about the number of slices per service request is not uniform among all the services. And okay, I'll go through quickly. Okay, so keeping those system model in mind, we have this solution, that is deep reinforcement learning based service distribution. Previously, we worked with Q learning approach, and we found that it is a bit that table itself is pretty long, and that queue table is really very big. So uh, we keep it. We found it hard to accommodate that queue learning or that queue table into the memory. So we come up with the deep queue learning approach, where the state space is nothing but uh, where the slice is currently assigned. If it is assigned to fog node, then the state will be something like this. Uh, Sorry, if it is assigned to fog node, the state will be something like this. And if it is assigned to cloud node, then the state will be something like 0, 1. So combining the state of each, all the slices and all the service requests, we can calculate the state space of, we can calculate the total state space. And the action is nothing but where we are assigning. So if we are assigning to fog node, this is one action. If we are assigning to cloud node, this is another action. So these are the two different actions we have. And based on the actions, we have the agent in the deep reinforcement learning will get some reward, and the reward will be something like uh, different. So if the slice is assigned to cloud, the reward will be something different. If the slice is assigned to fog, the reward will be different. And by combining these two rewards, we can calculate what is the total reward the agent will get. And the rewards will depend on the communication latency and the computational latency, and we can say it is like the service latency. So the reward, when we assign a slice to the cloud, the communication latency is nothing but uh, what is the RTD value, or what is the round trip time between user and fog and cloud. So if you combine both the things, it will become like communication latency. Whereas if we say what will be the computational latency, then the number of uh, then we can see like this the amount of resources it is using and the amount of resource it is demanding. Based on that, we can calculate the computational latency. And also during that time, we will see what is the communication latency between fog and cloud. Whereas if we go to the other side, what will happen, or what will be the reward when we assign the slice to the fog node? At that time, probably the communication latency, it is become like what is the RTT between user and fog node. But if we'll calculate the computation latency between I mean the computation latency, if we assign the slice to the fog node, and then it will become like what is the what is the resource demand of that services or of that slices, and then what is the resource allocated to that one. So based on that, we can calculate the computation latency. So if we combine both communication latency and computational latency, then we can calculate the reward of the assigned SL slice. So combining both the reward of communication latency and computation latency, we can see what's the reward when the slice is assigned to a fog or cloud node. So we have seen what's the performance. We have observed what is the result, the experimental result. And for the we have used the Python version 3.6 and Python version 3.6, TensorFlow 2.0 as the machine learning framework. We have used Keras at the top of TensorFlow. And these are some of the simulation parameters. And these are some of the simulation parameters related to the resource demand and resource availability. And regarding the result, we have compared this one with our previous work, which is entirely based on the queue learning. And we have compared this one with what is the percentage of slices assigned to fog node, and what's the percentage of slices assigned to cloud node. And we found that with the deep reinforcement learning, it is assigning less number of fog node without compromising the other constant. And along with that, we have also compared the success rate with varies number of slices. So here we are varying from 3 slices per service request to 5 number of slices per service request. And uh, along with that, along with the success rate, we have observed what is the CPU demand distribution between fog node and cloud node. What's the memory resource demand distribution between fog and cloud node. That means if what percentage of the CPU demand are fulfilled by the fog node, and what percentage of the memory is fulfilled by the fog and cloud node. And we have observed that the fog node is responsible for lesser percentage of resource demand fulfillment. So we found that the proposed solution is giving us better result as compared to our previous result, which is entirely based on the Q learning approach. And yeah, so if I conclude the whole work, then we have provided a DRL based service dispersal approach for fog and cloud computing, and where the service requests are processed by both nearby fog and cloud computing. But service mainly will be delivered by the fog node only. The deep reinforcement learning we have used to assign or to distribute the slices between fog and cloud. And our goal of using this DRL and addressing this problem um, is to assign or is to disperse the minimum number of slices to the fog node, so that it can accommodate maximum number of user without compromising the quality of service. And we have also seen what's the success rate of this approach, and what's the percentage of slices assigned to fog and cloud, how the resource demands are fulfilled by fog and cloud. And also there are other matrices we have seen from the simulation result. So this is all about our paper on an efficient service dispersal mechanism for fog and cloud computing using deep reinforcement learning. And thank you very much. If you have any questions, you can reach out to us, and you can see the introduction slide. You can get the email ID. You can reach out to us if you have any questions, or you can directly email us. Thank you very much.